So here we continue with section 7.3. And in this section, we're just going to go over some rules that allow us, or some theorems that allow us to take the Laplace transform and the inverse Laplace transform of more complicated functions. So suppose, for example, that I know that f of s is the Laplace transform of some function, f of t. And I can find that Laplace transform. And a is just some real number. Then if I want to find the Laplace transform of the multiplication of e to the at times this function f of t, then I can do that by this theorem, because it tells me that that's equal to f of s minus a, where basically I take the Laplace transform of f of t and I shift it. Instead of having wherever there's an s, I use s minus a. This is equivalent, of course, as taking the inverse of this right-hand side of f of s minus a, the inverse Laplace transform is what I mean. If I take the inverse Laplace transform, then I get exactly what's inside here, e to the at f of t. So, for example, if I have the function e to the 3t times cosine of 2t, well, I know the Laplace transform of the cosine of 2t, so what I have to do is find the Laplace transform of the cosine of 2t and switch s to s minus 3. And then, of course, I get s minus 3 over s minus 3 squared plus 4. So that's the first translation theorem. Now, for the second translation theorem that we're learning in this section, we need to understand what a unit step function is. And a unit step function, basically what it does is that it erases anything that is between 0 and a. So if I look at the unit step function, u of t minus a, then that tells me that it's going to be 0. This function is going to be defined to be 0 on the interval starting at 0 and ending at a, and then it's going to be 1 from a and on. And you can see the picture of the graph right here on the right. The reason we use those is that I can take that function and multiply it times any other function, say f of t, and what I obtain is the same function f of t, except that I get the portion between 0 and a gets erased, or I get 0 on that portion. Okay, so the second translation theorem basically says, again, I have f of s is the Laplace transform of a function f of t, and a is, in this case, a positive real number. Well, then if I have something a little complicated like this f of t minus a, some function that has been shifted, times a unit step function, then I can use this theorem to say that, well, the Laplace transform of that, this multiplicative f of t minus a times u of t minus a, is exactly e to the minus sa times f of s. Again, f of s is the Laplace transform of the function f of t. So if I think of this function prior to it being shifted to t minus a, then I can find its Laplace transform, that's f of s, and then I multiply that times e to the minus sa, and I get then the Laplace transform of this multiplication of f and u. Again, we can think of the other side as being equivalent. I can take the inverse Laplace transform of this function of s, e to the minus sa times f of s, and get then this complicated, maybe a little more complicated function of f of t minus a times u of t minus a. The key thing in this section, I think, is to understand when to apply which theorem. And so two features of the second translation theorem is, of course, if you see a u, then you know that you should be using the second translation theorem. Also, the exponential appears as a function of s, whereas there's an exponential that appears in the first translation theorem as a function of t. So there's a difference. That's the difference between the two. So I'll go ahead and stop here, and you should look at the example videos to see a few more examples of how we can utilize these theorems.